Hi, everyone. So I'm going to give a quick disclaimer here. There's going to be a lot of code in this talk. Don't try to read every line and understand every line. That's not the point. I'm going to show you how to implement type inference in Haskell, but I'll upload all the code and all the slides and the material, so don't get hung up on some little detail. Just go with it. All right. So I'm Christoph. I love types. But I hate typing, and the worst is when I have to type types. So let's learn about type inference so we don't have to type these types. So if we look it up on Wikipedia, it tells us that type inference refers to the automatic detection of the type of an expression in a programming language. The three things that we'll be looking at here are expressions, types, and the detection part. But as it says here, we need a programming language before we can do any kind of detection. So let's start by defining our expression language. So we'll be implementing type inference for a version of the lambda calculus extended with let bindings, integer literals, and Boolean literals. So we already saw the lambda calculus before, so let's run through it. I've got a couple of example expressions. So one is a valid expression, lambda x to x, so this is the identity function. It's also a valid expression. And I can do a let binding, for example. I can let bind the const function and then apply it to one and true, and it also is a valid expression. So if we look at that like a grammar, we've got int literals, Boolean literals. We've got variables, which is just variable names. We've got application, which is two expressions, one of them being the function and the other being the argument. And the space in between means we apply the argument to the function. The function to the argument. And we've got lambdas, so backslash, the variable name, and then an arrow to the body of the lambda. And the last construction is the let binding, where we have a binder, x here. We assign an expression to it, and then we're allowed to use that binder inside the body of the let binding. We're going to do type inference, so we also need types. Oh, sorry. First, let's define that in Haskell. So it's just we're gonna build that as an ADT. So first, we're gonna create a data type for literals. So one and true and false are our Boolean and integer literals. We'll define a constructor for variables, which is just hold text, the variable name. We're going to define a constructor for application where we have two expressions, one is being the function, the other one being the argument. We're going to lambdas are defined with a text, which is the variable name that is being bound, and the expression in which that variable can be used. And lets are defined using a text, which is the binder, the expression, which is assigned to that binder, and then the expression, which is the body. So for types, we've got int as a primitive type. We have function types. So for example, this is a function from int to bool. Bool is our other primitive type. And we've got type schemes, which is types where we quantify type variables using this for all sign. So this is the type of the identity function. And we can have types where we quantify multiple types. So this is the, for example, here we've got for all AB, function A to B to A to B. And that's the type of function application, if you've not seen that before. So how do we define our type language? It's simpler than the expression language. So we've got our two primitives. We've got the int type and the bool type. We've got type variables, and we've got function types. And then, because we need to, the quantification part is missing, we're going to define schemes, which are not types. They're called type schemes. We're going to define types as either being a type or a type with quantified variables in front of it. So here we see the for all binds the A1 and A2 and AN type variable inside the type T. When we define this as a Haskell data type, we've got two constructors for our primitive types. We've got a constructor for type variables, again, just text. And we've got a constructor for functions, which is the argument type and the result type of the function. And then for schemes, we're just going to use a single constructor here. And we'll say that when the list of variables that are being bound is empty, that's just going to be a type without, well, that's just going to be the type construction on the right, essentially. So now that we have expressions and types, we can look into type inference, which is the process of determining the type for an expression. And we can do this by just by ourselves. for now, to get an intuition. So if I give you the expression 1, that has type int. If I give you the expression true, that has type bool. If I give you the expression lambda x goes to x, the identity function, that has type for all a goes to a. We can define the const function, which is for all a goes to b goes to a. Right? So x has type a here, y has type b, and we return x, so that's type a to b to a. We can also define terms like this. So here we have a lambda, and x is the argument, and then we apply the argument to 1. So the type of this expression is lambda from int to b to b. Okay, let expressions. If I bind x to 5 and then I say in x, that's just of type int. If I define a function, a let binding where I bind a function and then apply it, here I define the identity function, I apply it to a Boolean literal, so I get a bool. And I can also just define the ID function and return that, which should give me for all a goes to a, right? So now we have like an informal understanding or idea of what we want to achieve here, and now we need a formalism or a notion to think about this in a bit more concrete terms. So we're going to use typing judgments here, which Vitaly already introduced. And the typing judgment in the type system or language we describe will describe a relation between a piece of syntax and its type. So the way we write this, the notation is like this, and everything below the line, that's the thing we'd like to show, and everything above the line are the things we need to show in order to show the thing below the line. So here, in order to show C, one needs to show A and B. And let's try doing that for the lambda as an expression here. So we've got two types here. We've got the type of the binder, we've got the type of the body, and then the whole expression has the type of a function from type of binder to type of body. That's the idea of our idea of a lambda. So what we'd like to show is that the entire expression has the type binder to body, and what we need to show for that to be true is that we need to show that the body has the type body. But we're missing something here. We're missing the ability to use the binder inside the body. And so that's why we need to introduce context so that we can capture that fact. And so a context is a mapping from a value level variable to type schemes. So mappings from value level variables to type schemes. The way we write this is using capital Greek letters. We only need a single context for this type system, so we're just going to use the capital letter gamma. And you write it like gamma and then the little dash thingy, and then the assumption in which that which needs to hold inside that context. So the way this reads is that in the context gamma, x has type ty1 here. And the way we implement this in Haskell is just by using a map from text to schemes, so the text is the variables. And now we can fix our judgment for lambda abstraction. So if we want to show in the context of gamma that binder to body has type binder to type body, we need to show that body has type body in the context gamma extended with the binding for the binder. So we have binder at type binder, and inside that context we need to show that the body has type body. So the way we need to think about infer here is, like, the first idea we had was that we'd go from an expression to a type, but there's actually a context, and we're also going to return that type in a monad because implementation details, unfortunately, because we're not doing math here. So we're going to define a TI monad here that just counts ints for us. It's not really important. Just think of this as whenever we call new tyvar, that function, we get a variable that has a unique name that doesn't appear anywhere else in our program. So this way we don't need to worry about shadowing here. So again, don't worry about it too much. You'll see how it's used now. So now we can get to implementing this inference rule. So this is the thing we'd like to show. So the first thing we do is we pattern match on the expression type, pattern match our binder and body out. We know what we want to return, so we're just going to say we want to return the type function from type binder to type body. Now we don't know anything about the body yet, so we're just going to create a type variable for it. It's a new type var. And then we're going to create the context from the old context that we've been given as an argument here, and we're going to insert the binding to the binder into that context. And then we're going to infer the type of body inside that temporary context. And now if we go and apply this, we can try to infer the type of this expression over here, which is lambda f goes to const 1 of f true. And if you know the const function, it just ignores its second argument. So the type of the body here is just going to be int. But that's not sufficient, because there's another piece of information here, and that is the second argument to const, where we apply true to the function f. And we'd like to capture the information, because if we look at this, we can learn that f needs to be a function, and f takes as its first argument a Boolean. So just having inferred just return the type is not enough. We need more information, and that additional information so that we can infer this type that we'd like to have. Right? And that additional information are we going to pass through in a type called a substitution. So we need infer to return additional information, which is a substitution. And a substitution is a mapping from type variables to types, as opposed to the context, which mapped value level variables to schemes. The way we write this is using this list-like syntax, and then we have pairs in there. So we have a pair here of var1 and ty1. So var1 maps to ty1, and var2 maps to ty2. And the way to implement this in Haskell is, again, just a map from text, which is the variable names, to types. There are two operations on the substitutions that we need. One is applying a substitution. We can apply substitutions to types, schemes, and contexts. And the way you apply a substitution to a type is by replacing all type variables inside that type with their mapping in the substitution. And to get an intuition for that, we're going to do a couple examples again. So here I have the substitution that maps a to int, and I apply it to the type a, and that gives me int. If I apply that substitution to the type a goes to a, I get int goes to int. If I apply that substitution to the type a goes to b, I get int goes to b. So variables that do not appear in the substitution remain untouched. If I apply that substitution to the type for all a goes to a, I just get back for all goes to a, for all a, sorry. Because it's bound by the quantifier, and so again, the substitution can't reach inside that. Think of it as a scoping operation here. And then I can apply a substitution which maps a to int and b to bool to a type which only guards the a, and then I can reach the b here. So this is a for all a goes to bool after applying the substitution. And so when applying a substitution to a type, we're looking at the implementation here. What we do is we say, if we're looking at a variable, we're going to look that variable up in the context. And if it's there, we're going to say, OK, that's the type we looked at. Like, the type in the context is the thing we're going to the type in the substitution is the thing we're going to return. And if it's not in the substitution, we're just going to return the type variable again. Types that don't appear in the substitution remain untouched. For the function type, we recurse into the function and the argument type. So we apply the substitution to the argument type, and we apply the substitution to the result type of the function. And literal types substitutions don't matter to literal types because there's no type variables in int or bool. When we apply a substitution to a scheme, we need to make sure that we guard all the variables that are quantified over. So what we do when we apply a substitution to a scheme is that first we delete all the variables that are being bound in the quantifier list from the substitution, and then we apply the substitution to the type inside. And when we apply a substitution to a context, remember a context is a mapping from variables to schemes. We just map the apply substitution function for schemes over the context. All right, the second operation we'll have on substitutions is composition. And the composition of two substitutions s and u is the same, applied to type t is the same as applying the substitution u to t, and then applying the substitution s to t. And the way we implement this is by unioning the two substitutions in a way that favors the bindings inside S2. But it's kind of a complicated implementation. The idea here is that we want to preserve the information in both of these substitutions, and that's what this does. So if you want to take a look at that in peace, please. For us, it just means we preserve the information we collected for substitution 1 and substitution 2. All right, and so now we can enhance our infer function for lambdas to its final form. So when we infer the type of the body, over here, we get back a substitution, and we return that substitution. We need to pass it back up in case we learned anything about type variables that someone else cares about. And we need to apply that substitution to the type binder so that we use all the information we figured out when we inferred the type of body on the type binder. So next is the inference function for literals. Literals are pretty simple because if I have an int literal, I know that that has type int, and for booleans I know that for type bool, and there's no substitution shenanigans going on here at all because there are no type variables, and the context doesn't matter either. So the next construction we look at is let, which is very similar to abstraction, to lambdas. And so we're going to look at this stepwise. Again, we've got two types here. We've got the type of the expression that is being bound. We've got the type of the body. And the whole expression has a type body. So when we build the typing judgment, we want to show that the entire expression has the type body. In order to show that, we need to show that expr has the type expr, and that the body, again, has the type body, but in the context extended with the type of type expr, because that's in scope because of the let binding. So again, we'll look at implementing this. So we'll start. We pattern match on the let constructor here. We get our components out. We know what we want to return, which is the type of body. We can infer the type of expr here. We can infer the type of type body, but first we need to construct the enhanced context again. We extend it with a binding to x. Then we infer the body inside that new context. And that's that. So the only thing left now is that we need to make sure we pass the substitutions so that the information flows through. Right? So we get a substitution back when we infer the expression. We get a substitution back when we infer the type body. But before we do that, we need to apply the substitution to the context here. So in case we learn anything about type variables while we infer the expression, we want to make sure that's available when we infer the body. And then we need to return the composition of the two substitutions we found as to not lose any information. So now we're looking at the var construction, which is the simplest in terms of its inference rule. So if we just have a var, there's only the type of the var, and we can find that type of the var by looking it up in the context. Now mathematicians don't worry about the case where the variable does not appear in the context, but we have to. So when we write this code in Haskell, what we do is we look up the var in the context. If it's not there, we need to throw an error. We need to say, well, there's an unbound variable here. So if you say, right, lambda x goes to y, we need to say, well, what does this y mean here? And if we find the scheme, we're just going to return it. But that doesn't work because inference returns types and not schemes. And so we need an operation that takes us from schemes to types. And that operation is called instantiation. So we instantiate a scheme by replacing all the bound variables for that type scheme with fresh type variables. So as an example here, we've got the function type for const, right? For all a goes to b goes to a. And then after instantiation, we've just got type variables here. There's nothing that's bound anymore. And the idea here is that if I have the type for the identity function, which is for all a goes to a, and I want to apply that to, say, an int, I have no way of getting a substitution to make that a an int unless I first instantiate, and then I can reach inside that type and change the a to be int. I also need to make sure that the next time I want to use the identity function, I don't assume it has type int. So that's why we need to pick fresh variables every time we use this. And the way we implement instantiation is that we create a new type variable for every var that has been bound in the scheme. Then we zip it together, the new type variables that we created with the vars. And remember, vars are just text, that's just the variable names. And our new vars are type variables, so we have a mapping from text to types that is a substitution, and then we can just apply the substitution to the type inside the scheme. And that's instantiation. So now we just insert that call to instantiate here and return the type that has been instantiated. And that's the variable rule and its implementation. So now the last construction in our language is application. So in application, we've actually got three types. We've got the type of the function, the type of the argument, and the result type. So if we want to infer the type of the function application to be type result, we need to first show that the function has type fun. we need to show that the argument has type arg, and then there's an additional piece of information we have, which is that the type of function is type argument to type result. And we're going to need to use that piece of information to tie these together. All right, so we'll try to implement this as usual. We pattern match. We know what we want to return. We want to return the type of result. We don't have any information about it yet, so we create a type variable for it. Then we go ahead and infer the type of the function. We go ahead and infer the type of the argument. And now we have a problem, because somehow we need to use that relation we thought of before. But that tyres is in an unfortunate spot over here, where we can't really do anything with it. And so the operation to relate these with one another is called unification. And so we need to write the unify function here. And when we unify two types, what that means is that we find the substitution that we can apply to both of these types to make them equal. Mathematicians will make sure to say that it's the most general substitution, but that doesn't matter for us, because when we're implementing it, the easiest implementation is the one that gives us the most general ones. And so the way we write this is that we say A unifies B with this funny U, and for now we're just going to say that equal is the substitution that makes them the two equal. That's not mathematically correct, but for us it's enough, because we can get an understanding of what's going on. So if I unify the type A with int, what I get is a substitution that maps A to int. If I unify the type function from A to int with bool to int, what I get is a substitution that maps A to bool. If I do that the other way around, I get the same substitution, because unification is commutative. So I can swap the two arguments around and it doesn't matter. And then there's this case where if I unify the function A to B with the function B to A, I need to make sure that I only map A to B or only map B to A. I can't map the two with one another, because then if I apply it to both sides, I'll end up with different types. Right? So that's going to be important for implementation. And because the last case seemed tricky, we're going to have a helper function that helps us bind types to variables. We're going to call it var bind. And it's going to take, as its first argument, the variable that we want to bind the type to and the type. And so the first case we'll consider is when we try to bind a type variable to itself. And that just means we need to return the empty substitution, because there's nothing to do here. The second case is what happens if I try to bind a type to a type variable, but the type contains the type variable again and is more complex than just the variable itself. So the first binding would also kind of satisfy the problem where the type contains the type variable, but if they're equal, I can just return the empty substitution. But if I have a type like this, that's a problem, because that would yield some kind of infinite or recursive type. We don't have that. So we need to forbid that that happens. So we check if the variable is a member of the free type variables of that type, and then we need to throw an error, and that check is called the occurs check, if you read the literature. So you know that that's the case that you need to think of. And in any other case, I'm just going to bind the type B to the variable A. Right? So I just return a singleton where I map the type variable var to the type ty. Now that I have this helper, we can implement unification for all types. So unification. The first two types that we can unify, if I get a type of int and a type of int, that unifies with the empty substitution. I don't need to do anything here. If I get the same goes for bools. If I want to unify two function types, what I need to do is I need to unify the two argument types, and I need to unify the two result types. But unification returns a substitution. So when I unify the argument types, I gain information. So I need to make sure to carry that through, right? So again, I apply the substitution to the result types, unify those, and then I pass back the composition of the two substitutions I gained, again, not to lose information. The variable case is here. That's where we use our var bind function. And see that there's two clauses here. That's because, as I said, unification is commutative, so we need to make sure we cover it both way around. In any other case, we get a unification error, which you might have heard before if you've used a functional programming language or a language with a type checker. And so that's that case. If you give me an int and a function type, there's no way I can make them equal. There's no substitution that would satisfy that, so I need to throw a unification error. Same goes for int and bool, right? And so this is the last piece we need to implement application. the inference for application. So now I can use the constraint I figured out over here, that relation. I can say I need to unify the type of function, as you see, with the type of tyfun from tyarg to tyres, which is exactly this relation. All right. Only thing that's left to do is thread the substitutions through. So we get a substitution when we infer the type of the function. We get a substitution when we infer the type of the argument, but we need to make sure that we use the information we found when we infer the function. And now when we unify, we need to go back, because we might, when we were inferring the argument, we might have found something out about the function. So we need to feed that information back and say, apply the substitution that we found here to the type of function when we unify. And that gives us the third substitution. And then we need to collect all that information up. So we compose all the substitution we gained and return the composition and apply the substitution we figured out when unifying so that we can get the proper type for type result. And that's actually the entirety of this of the inference algorithm for the type system we described. We do have 9 minutes left. So we might be able to do a bit of a demo. I would actually run this thing. So that's the thing we have over the mathematicians. We can run our things. But again, we've implemented, like, this is a fully functional type inference algorithm for the core of a lot of functional programming languages that you've used. And it's about around 120 lines of Haskell, the core inference algorithm. The parser and all that is kind of, I mean, that takes space, but the core algorithm here is pretty simple, or it's not simple, but it follows like a pattern that you can follow. If you see a typing rule, you kind of have an idea of how to approach implementing that now. And so I'll have tons of resources, and the paper that initially outlines the algorithm that I'm using here, which is called Algorithm W Step by Step, and I'll also link the initial paper, which is called Principal Type Schemes. I think the more practical approach is easier for a programmer, and then go back to the theory. So first implement it, then understand what you just did, basically. All right. So we've got 8 minutes. Would you prefer to spend that doing questions, or would you like to see some type checking? Yeah, I thought so. All right, so let's do some type checking. That's the wrong folder. All right. So one thing I can say, I've predefined a few functions. So if I type identity, I define that to be the identity function. If I type const, I've already predefined that one. And so one example that we had, right, was this one, where we said a lambda f goes to const 1, and then we had, I think, f of true, right? And so we wanted that to say that returns a function from bool to a goes to int, right? So that seems to work. The occurs check. This is what happens if you do this. That's not a valid term. In the untyped lambda calculus, it's happily going to take that, but if you try to type that, that's a problem. That doesn't work. So it's good that we catch that, because that's also not a valid program to run. I mean, this is easy enough. Can you define a fixed point? Wait, let's try. I haven't implemented generalization, but let's see. So let's, wait, how do you do that again? X equals f of x in x? No, wait. Oh, I don't have recursive binding, so how do I do that even? Yeah, sorry. No, sorry. I think I can't. We can define like a function here, which, oh yeah, I've predefined things like add, for example, right? So I can say let add 3 equals add 3 in add 3 apply to 4. So that's just int. And if I say true, that's unification error, because I can't unify type int with type bool. So I didn't lie to you. Like, this code actually does what it says on the covers. Is there any other expression you'd like me to try? All right, that's good. All right, so I think that's that. Thank you very much. Yeah. And oh yeah, I'll put all this stuff in that repo. It's private right now, but once I've, because I have the finished slides now, I'll put everything in there and put it online. So.
Okay, thank you, Christoph. Questions?
It was quite dense. Thank
Yeah.
you. It was and very interesting. Question probably not directly related, but is it easy to extend it to support type holes? So I mean, I want to find a type I can use in some place instead of a variable.
Yeah, so the way that works is that you have like a special construction in your expression language, right? And once you reach the unify step, right, you're going to have a typed hole that is being tried to unify to some type. And then you can say at that point, oh, now I know what type my typed hole needs to have.
So I will get the substitution.
No, you'll get to unification. You get a substitution which maps your hole to some type, right? And you look the hole up and you figure out the type that your algorithm expected it to have, right?
Okay, anyone else? Anyone?
Hi.
Hi.
I didn't get why so in the step of type inference for function,
Yes.
you write a separate line, type fun equal type arc to type res, and why it isn't on top of the line? I mean, where we have context constraints. Is it some different kind of constraint?
There is no expression in here that has the type fun. The type tyres, right? Because you only get the type tyres once you apply the argument.
Mm-hmm.
So the only thing you could write is that fun arc has type tyres, but that's below the line because that's the thing you actually want to show.
Okay.
Right?
Uh-huh.
So if you just wrote that thing above the line, you could show something by showing, like you'd be defining something in terms of itself.
Okay. Okay. Got it.
Right?
Thank you.
Thank you very much for your talk. The question is, in like real-world language, you sometimes have some definitions that use the definition that would follow
so like recursive
after that. So for example, you had defined a function that uses the function that will be defined in the end of the file.
Yeah.
How do we do the type checking in this
all right.
situation?
So the way that works in a compiler is that you do something where you compute something which is called binding groups. So before you get to type checking, you figure out the dependencies between the things. And then if your language allows you to define things recursively, like Haskell, for example, these need to go into a single binding group, and then you infer that at once. Right? So
That's can I read somewhere like?
I just Google for binding groups, or like the PureScript compiler is actually quite good. So maybe I'd just read that desugaring pass, because that was where I learned it from essentially. So
Thank you.
right.
Any more? Okay. Thank you, Christoph. That was great.
Thank you very much.